Welcome back. And now and again you have to give a presentation. If you're a student or if you're a staff member in a university, you have to give presentations every day. In business, you have to give presentations. So why not get a machine to do your presentation for you? We hear a lot of that sort of thing. And I thought maybe I'd give it a try and see if software lived up to its expectations. So I'm testing out one of these, which is called Tome. It's really Tome.org. It's Tom with an E on it, so it's very easy to Google Tome. And you get either a free number of tokens, and for me that was just enough to make one batch of slides, and that's it. Or you can pay some money to get a little bit more PDF and so on of your presentation. At the moment mine's just on the web page. It doesn't seem to give you PowerPoint slides for some reason. So because this is an engineering forum that I'm on here, actually, I thought really I should put something to do with engineering rather than the arts or normal sort of storytelling or business or whatever. So I asked it to give me a presentation on Wiener filters. And I basically just said, write me some slides on Wiener filters, whatever. And I'll show you what it gave me. It was interesting, but I'll comment as we go along. So it called itself the Unleashing the Power of the Wiener Filter. Let's see if we can just click on that. Okay, so here's my presentation, or the presentation of the software, Unleashing the Power of the Wiener Filter, and here's the first slide coming up. And in common with many people who give presentations, it's actually split the talk into various stages and says I'm going to be talking about introduction, then what is a Wiener filter, applications of Wiener filtering, and so on and so forth. Personally, I don't like that way of presenting talks, because especially with small ones, because with small talks, the talk's over, in about 10 minutes anyway. It was a really small talk. There doesn't seem to be much point in listing everything. You just get into it as you're going along. And with a long talk, if you do that and you maybe number them and say, I'm going to be talking about 1 this and 2 this and 3 this, you find yourself in the audience going, oh my God, he's only at number 3. I'm only halfway through the talk and I've got to suffer another half an hour of this. So I don't think that's a great idea, but okay, I accept that it's a recognized way of doing things. So here's the first real slide, Introduction to Wiener Filtering. The first thing you'll notice is that it's put this rather cool looking picture, and you have to think, well, where on earth did it get that picture from? Either it created it itself or it got it off the internet. It may have got it off the internet, of course. Whilst I accept it's a very cool looking picture and real sci-fi looking, it has got nothing to do with Wiener filtering. So that why put it there? I mean, a picture of Norbert Wiener or something might be better, or a block diagram of something, if you're an engineer or a scientist anyway. Anyway, it goes on, Introduction to Wiener Filtering. Wiener filtering is a powerful signal processing technique that allows us to extract useful information from noisy signals. I would say signals from signals plus noise, but I think we know what the person's saying here, or the AI is saying rather. It was first introduced by Norbert Wiener. By the way, those of you that think it should be Wiener, it probably should be Wiener, but his pronunciation. But he was American, and so he liked his name to be pronounced Wiener, I believe. That in fact, a friend of mine, rather old friend of mine, who used to work with him when he was quite young, a long time ago, said that that's how he liked his name to be pronounced. So Norbert Wiener in the 1940s and has since become an essential tool in many fields. The English is pretty much perfect. There's no problem with the grammar or anything, including image processing, speech recognition, and communication systems. And the basic idea behind the Wiener filter is to estimate the underlying signal from a noisy observation. That's all right. By taking account the statistical properties of both the signal and the noise, that's perfect. This estimation process involves minimizing the mean square error, again, perfect, again, between the estimated signal and the true signal. And another cool image, and again, nothing to do with Wiener filters. Wiener filtering is a linear filter used to remove noise from a signal. It's based on the assumption that the signal and the noise are statistically independent. And again, that's correct. Although you can get around, you can actually derive it with the noise terms, the driving noise and the process noise, it's called in Kalman filtering, and the additive noise are correlated, but usually we assume they're not. The Wiener filter works by estimating the power spectral density of the signal and the noise, and then using this information to construct a filter that minimizes the mean square error between the true signal and the filtered signal. Again, pretty much perfect. The resulting filtered signal has reduced noise and improved signal quality, so it hasn't sort of overestimated things. It says reduce noise, it doesn't say zero noise or remove the noise completely or anything silly like that. And yet another space age picture. It looks like we're in 50 years in the future or something, or a different planet. Again, probably nothing to do with Wiener filters, but applications of Wiener filters. Wiener filtering is a wide range of applications in image processing, speech recognition, communication systems. It says in image processing, it's used to remove noise from images, enhance image quality, and restore blurred images. In fact, the blurred images is quite old, really. Goes way back. In speech recognition, it's used to improve the accuracy of speech recognition systems. Often, the Wiener filter, of course, is part of adaptive filters. More importantly, finite impulse response filters. It doesn't mention any of that, of course, but anyway. In communication systems, Wiener filtering is used to remove interference caused by other signals, reduce noise in the received signal, and improve the quality of the transmitted signal. And so these are all quite generic terms, and they're all correct. It's used in radar and sonar, yes, to detect and track targets in noisy environments. I can't say I'm an expert in radar or sonar, but I assume that's probably true. One of the advantages in Wiener filtering is its ability to reduce noise while preserving the important features of the signal, and again, that's correct. Makes it particularly useful in applications where high signal to noise ratio is required. Well, that's actually required most of the time anyway. As engineers, you really want to have high signal to noise ratios, such as in medical imaging or audio processing. Another advantage is its simplicity and efficiency. I wouldn't say it's that simple, to be honest. Well, it wasn't originally when Wiener first thought up the theory. In fact, nobody could understand it at all, actually, at the time, because it's kind of quite common now. It appears in a great many books on statistical signal processing and signal processing. It's even in my own book, Rudiments of Signal Processing and Systems. It can be easily implemented using standard signal processing techniques. Well, that's true, because the filters usually are an FIR filter at the end, or an IIR filter, pole zero or all zero filter, and in fact very easy to implement on a microprocessor once you've got the trouble of working it out. But of course, it can also be done with fast Fourier transforms as well. That's another way to do it. And the limitations of the Wiener filter, and here we've got a really spaced out looking image again. It looks like it's one of those things from Star Trek. I can just imagine Scotty in there, trying to fix the some such and such relay system that's broken down or something. And the Enterprise is about to blow up in about 10 minutes or something. And Captain Kirk's telling him to hurry up. And he's going, "I'm going as fast as I can, Captain. It kind of mix matter with antimatter, cold, whatever." But I can't quite see the relevance to Wiener filtering, but nevertheless, it's put that in there. Despite its many benefits, Wiener filtering has some limitations and constraints. One of the main limitations is that it assumes that the signal and noise are statistically independent, which may not always be the case in real-world scenarios. Well, actually, I've yet to see a real-world scenario where that's not the case, funnily enough, so I think Wiener did get it right. But even if it isn't, there are as I say, that you can modify. It's not that hard to modify the Wiener filter if you knew what that correlation was, like a sort of transfer function relating the two noise signals. It does come about, I suppose, in adaptive filters, that it's sort of the geometry of some adaptive filters when you're setting out multiple microphones arrays and stuff like that, but that's sort of at a different level. Another limitation is that Wiener filtering can only be applied to linear systems. That's true. Well, it's a linear theory. Nonlinear systems require more advanced filtering techniques, such as Kalman filtering or particle filtering. And again, that's true, though there are adaptive style least means square type algorithms which are nonlinear, kind of loosely based on Wiener's ideas. So it's not completely true, but it's pretty standard. And then the ubiquitous conclusion, of course, it's actually put in conclusion. I always tell people not to do that. If you got conclusion, we know it's a conclusion, so don't put in conclusion. But nevertheless, in conclusion, Wiener filtering is a powerful signal processing technique, and so on and so forth. And another cool picture, it looks like you've reached the 7th dimension or something. Really amazing, but again, what's it got to do with Wiener filtering? What would I say about these 8 slides? Well, apart from more like 7 slides, because the first one's just the title. 8 slides. Well, it's quite generic. I mean, it's factual. It's not. It would be like if a student gave this, would depend on the what the year was and so on and so forth. But it'd probably be like a C, some kind of in the C range. It would be a pass, definitely. Information's there, but it's very generic. There's no block diagrams showing signals and noises and transfer functions and power spectra. There's no equations in there anywhere, which you really need in engineering or science type presentation, unless it's to a general audience. If this is to a general audience, it might actually be too complicated for a general audience even. So I would say it needs more to be good. But having said that, this was generated by a machine. There's no human input at all. It's grabbed all the information, and it's factually correct at least. So I'm quite impressed with that. I believe you can change the pictures, so it's not like they're written in stone or anything like that. So if you compare with like a year ago, where of course AI existed, but these kind of things didn't exist. Everything seemed to come in a great big cluster around the October, November last year, and eventually ChatGPT came in, and DALL-E was there before, and now we've got a plethora of such software available. So worth a try, I would say. Unfortunately, I've run out of credits, so I'd have to subscribe to try it again. I'd say it's got promise, and I'm sure some people will try and use it. So thank you very much.